Hi, my name is Emily First, and I'm a PhD student at the University of Massachusetts Amherst. Today, I'm going to talk about my paper, Diversity-Driven Automated Formal Verification, which is joint work with my advisor, Yuri Brun. This work presents a tool called Diva that automatically synthesizes proofs of software correctness that prior tools could not. Diva leverages the diversity in different models of proofs to verify more properties of software systems automatically than ever before. And with that, I'd like to tell you why you should care about automating the formal verification of software. Formally verifying software is important because software touches almost every part of our lives. When software is buggy, sure, maybe it's just a simple inconvenience for you, or it just costs companies more money. But in high-stakes domains such as aerospace engineering and medical devices, buggy software can cost people their lives, and so it is critical to prevent that. A promising method for building correct software has been to use programming languages that are designed to support verification, called interactive theorem provers. This includes languages such as Coq, Isabelle, and Agda, among others. Coq is the language that we focus on in this work, since it is used in many software verification efforts. With Coq, a programmer can specify a theorem about a property of their software and write a proof script, which is a series of proof tactics, such as induction and reflexivity, that Coq uses to attempt to construct a proof of the theorem. You've managed to complete the proof if you're able to get to QED. These interactive theorem provers have already had a significant impact on industry. Airbus uses the verified CompCert C compiler to ensure safety and improve performance of its aircrafts. Chrome, Firefox, and Android use formally verified cryptography libraries to secure communication. Amazon, who is one of the sponsors of this research, successfully applies formal verification to cloud security problems in Amazon Web Services, providing tools for users to detect entire classes of misconfigurations that can potentially expose vulnerable data. Other companies have also been successful in using interactive theorem provers to provide formal verification as a service to clients, from building solutions for healthcare, infrastructure, and financial domains, to formally verifying smart contracts, to verifying hardware design. Still, even with the help of an interactive theorem prover, the effort required to write proofs is often prohibitive. Imagine spending a lot of time writing thousands of lines of code to get a functioning piece of software. Then, if you thought about verifying that code, it would require even more time and a lot of proofs in proportion to the code you just wrote. Consider, for example, the Coq-verified C compiler CompCert. The proof is more than 8 times bigger than the compiler code itself, and took 3 person-years of work. So as a general rule, because of the great expense of verification, virtually all software the companies ship today is unverified. This brings us to automation. If we can cut down the time programmers would need to spend on writing proofs, that would be a big win, because we'd be making progress towards enabling more verification. Our tool Diva, together with prior work, has reached a new milestone of proving over 1/3 of all theorems completely automatically on the CoqGym Benchmark, which is the largest available collection of real-world Coq projects found on GitHub, with a test set of over 10,000 theorems. So I'll first talk about what prior approaches have done to contribute to this number before moving on to what we've done with Diva to improve upon it. In prior work, tools called hammers take a solver-based approach by performing efficient automated reasoning using mathematical facts from a pre-existing library to attempt to hammer out a proof. For CoqHammer is that tool. It doesn't generate proof scripts, but rather produces proofs in Coq's logic called Galena. And evaluated on the CoqGym Benchmark, CoqHammer can automatically prove 26.6% of the theorems. However, hammers are restricted by their precomputed facts and cannot reason about proof approaches such as induction, which greatly limits their power. To overcome the limitations of a hammer approach, researchers have used machine learning to model existing proof scripts to perform next tactic prediction. So here, we have a partial, incomplete proof script, could even be empty, that serves as input to a model that has been trained on a corpora of proof scripts, and it can predict the next likely step of the proof. But to increase our chances of actually being able to complete the proof, let's instead query the top k, or here 3, model predictions. Those predictions can be applied to the proof script, giving us new candidate proof scripts that can be in turn fed as input again to the model. To do this more systematically, we apply Metaheuristic search, So here's the start of our search tree, and in metaheuristic search, the model is biasing the search towards the likely next prescript steps. So we continue the search until one of our candidate prescripts predicts QED, or the search times out. And yes, throughout it is possible to prune the tree and not explore some branches if they are not progressing the proof. But all that matters in the end is that we've been able to reach QED. Our work, including our prior tool TacTok, follow this overarching approach. TacTok's model uses the proof script and proof state together to predict the next tactic, and then biases search with those predictions. Importantly, the key results of this work was that TacTok is complementary to prior tools ASTactic and CoqHammer. ASTactic is a deep learning approach that considers only the proof state as input to its proof script model, and then performs metaheuristic search to prove 12.3% of the CoqGym test set, while TacTok proves 12.9%. Evaluated on the CoqGym Benchmark, we saw that together with ASTactic, TacTok can prove 20% more theorems, and together with CoqHammer, TacTok can prove 11.5% more theorems. The approaches in TacTok and ASTactic present new models to use in proof script synthesis through encoding information about proof scripts. The question remains, which model do we use? Do we use the one that has the best overall success rate? But what if that model doesn't prove anything that, say, CoqHammer doesn't already prove? What if the particular theorem you want to prove is proven by some other model? So our tool, Diva, explores using multiple diverse models and how to leverage the diversity in those models to enable more verification. Usually with multiple models, you think of ensemble learning, and in a typical ensemble learning setup, you have a set of models that differ in some way, and you consolidate their predictions and they vote on a single prediction to use. But one of the problems with ensemble learning is that typically the majority of models have to make the correct decision. If you have very diverse models and say only one correctly performs a particular task, the other models will drown it out and the ensemble will fail on that input. Even with stack learning, which picks the single best model to apply, picking out that model can be error-prone, and so stacks can improve but can also hurt performance. We overcome this problem in the formal verification domain. For the downstream task of generating a complete proof script, we can let each diverse model attempt to synthesize a proof script for a given theorem from scratch. The Coq proof assistant can then unequivocally tell us if a proof is correct, and so we can throw an army of models at the problem, and even if just a single one generates the proof, our ensemble can pick that proof out every time. So multiple diverse models and the existence of the proof assistant, a correctness oracle, mean that we do not have to sacrifice proving power, and we don't have to choose between models. This makes formal verification a fantastic domain for ensemble learning, if done correctly. And our results will show just how great this concept works. Now, what do we vary to create this diverse set of models that potentially prove complementary sets of theorems? Well, we can vary what aspects of the training data we encode, such as the proof script and the current proof state, and the learning parameters of the model itself, such as the learning rate and the embedding size. We implement and evaluate these variations in Diva, and so I'll talk now on how we go about doing that. We can encode the proof state and proof script in the same way as we do in TacTok, where the proof state ASTs are encoded using a tree LSTM, and the proof script sequence is encoded using a bidirectional LSTM. We also consider another aspect of the training data, the proof term itself, which is the underlying Galena object that is being constructed by Coq as the proof script is executed. We extract the current proof term after each tactic invocation. So, after encoding, how do we create this diversity? Well, we vary a bunch of things. For example, we can vary what information goes into the model. We can just model the partial proof script already written, or just model the state of the proof, such as what mathematical facts have already been proven and which ones remain unproven, or both. We can also model, or not model, the underlying Coq-generated proof term. Or we can directly alter how the model building happens. For example, we can control the length of the proof being modeled. We can have the model see only the single previous step of the proof, or several steps. We call this the sequence step parameter. We could also change the learning rate, which determines how much the model weights are changed in each training iteration. Or we can change the size of the model by changing the size of the embedding the model uses or the number of layers. Or we can change the order in which the training data examples are seen during training time. Now, with multiple models, if we give each of them 10 minutes to synthesize a theorem, it'll take a long time if we wait for each model to run before starting the next. We observe, however, that when a model is going to prove a theorem, it does so fairly early on in the search. So instead, we choose an arbitrary order and let each model run for a specified amount of time, trying to prove the theorem from scratch, interrupting its search to allow the next one to try, and cycling back to the first model. By using this method in Diva, we are able to cut down the mean time to prove a theorem by up to 97%. To train and evaluate Diva, we use the CoqGym Benchmark dataset, which has been used in several recent automated proof synthesis papers. The projects in this dataset fall into two categories: software proofs and mathematical proofs. The training set consists of 96 projects, which has over 57,000 theorems and their proof scripts. The test set we evaluate on consists of 26 projects, totaling over 10,000 theorems. Through varying aspects and learning parameters with differing values, we generate 62 models that together prove 21.7% of theorems in the CoqGym test set. Diva also is complementary to prior tools, proving theorems they were unable to prove. Diva is able to prove 908 theorems that ASTactic cannot prove, for a 77% increase, 842 theorems that TacTok cannot prove, for a 68% increase, and 781 theorems that Coq-Hammer cannot prove, for a 27% increase. Importantly, Diva proves 364 theorems that no prior tool was able to prove, for an 11% increase in theorems proven. This brings us to the new milestone of proving over 1/3 of theorems using Diva and CoqHammer together. We also evaluate which diversity dimensions are the most useful in increasing proving power, so that researchers going forward can consider them in their models. We found that including different training data aspects resulted in the most diversity of all the dimensions we considered, leading to the greatest proving power increase. Adding the proof script provided the most diversity, followed by the proof state. We also found that varying learning parameters resulted in significant diversity, and so a significant improvement in proving power. Varying the depth of the proof script sequence that the model learned from and the learning rate led to the greatest diversity of learning parameters that we varied. I will now place our research in the context of related work. As we saw throughout the talk, there are multiple tools for synthesizing proofs fully automatically, and others are discussed in more detail in the paper. There are many instances of machine learning models being combined using ensemble learning, and we have demonstrated a great application for it in the domain of formal verification. Metaheuristic search has been shown to be fruitful in many other software engineering tasks, such as for test suite generation and program repair, and we see that it is quite useful in proof script synthesis as well. And lastly, there are more advanced language models than what I mentioned today, and they are not only useful in natural language tasks, but also for code generation. In conclusion, I presented Diva, a tool that uses diversity to improve the proving power of proof script synthesis. Diva is publicly available. We thank NSF and Amazon for sponsoring this work. Diva proves 68% more theorems than TacTok and 77% more theorems than ASTactic, two prior proof script synthesis tools. Diva automatically proves 364 theorems no existing tool has proved. And together with CoqHammer, Diva proves more than 1/3 of all the theorems in CoqGym, which is the largest fraction to date. We identify a new application for ensemble learning by using the theorem prover as an oracle for optimally combining model results. Our work strongly suggests that using diversity for improving automated formal verification is fruitful and will enable automating more verification. Thank you.